So this is chapter 9. We are changing topics in a major way. We're going to start learning about energy. And energy is important in pretty much every field of science. So you'll see it again. Now let me just warn you, this chapter, chapter 9, is really preparing us for chapter 10. Chapter 10 we learn about conservation of energy, which is incredibly important, and other things. So this is just really preparing us for that chapter. All right, so here's the objective. Okay, so it's work and kinetic energy. And you're going to notice that in physics, the definition of work is different from what we would use in regular everyday English. Okay, so work and kinetic energy. Kinetic energy is energy in motion. We're going to use systems-based thinking to develop a model of energy, what it is, how it's transformed, how it's transferred. We'll introduce the concepts of work and kinetic energy. We'll learn Hooke's law for springs and the new idea of a restoring force. And you might think this is a total waste of time. Why do we care about springs? Well, we're really learning a differential equation that we're going to use in Physics 220 and you use in other fields of science. So that's why we're doing it. To introduce a model of thermal energy and dissipative forces, and then talk about power. All right, so first let's talk about something called the energy principle. So what is energy? What is energy? If you had to define energy to your 10-year-old brother or sister, what would you say? And so at this time, most of the students in the class, look confused, or somebody might say something like, it's the ability to do work. And so I always say, well, how come it's so hard to define energy? Well, the answer is because we don't really exactly know what it is. We know there's different types of energy, we know how to use it, we have equations for it, but we don't exactly know what it is, which is kind of interesting, right? So let's talk about some different types of energy that we'll see later. So, and I just want you to think of the most obvious form of energy, okay? So what kind of energy is shown there? You see a rocket ship moving. So it's moving, right? So that's kinetic energy, energy of motion. Now, I agree. I mean, you see other types of energy, right? You see thermal energy, heat. There's other types of energy, but I just wanted to get the point across. Kinetic energy is the energy of motion. Okay, here, what kind of energy does this thing have? Roller coaster cart people. Potential energy, right? It has gravitational potential energy. So potential energy has to do with position or location. And here you have this super hot horseshoe. So what kind of energy is demonstrated there? It's thermal energy, right? It has to do with, or heat, has to do with temperature. Now, we've been drawing force diagrams a lot lately. When you draw a force diagram, what's the most important? What do you first have to figure out, which is usually pretty easy? You have to figure out what the object is. Okay, well, it's different with energy. With energy, you have to talk about the energy of a system. It's always a system. And so you have to always figure out what the system of interest is. And everything outside that, we're going to call the environment. Okay? So here's this. I know I'm being really vague, but that's okay. We'll get more specific later on. So here's a system. And we say that the system has energy E sys. And everything outside the system, we're just going to say is the environment. All right. Now, within a system, energy can be transformed. And this is a situation or a place where you want to be careful of the words. So we're going to use transform, and then we're going to use later transfer. They're very, very different. So within a system, energy can be transformed. So here's an example. So right now, this marker has gravitational potential energy. When I drop it, the gravitational potential energy gets smaller and smaller. The kinetic energy gets larger and larger. So we would say that the gravitational potential energy is being transformed into kinetic. And you can see there's lots of different ways to do that, right? Kinetic goes to potential, kinetic goes to chemical, kinetic goes to thermal, there's all sorts of ways. But the important thing is, inside or within the system, energy can be transformed. Something else. Let's say I ignore air resistance. Let's say I have a certain amount of gravitational potential energy. Right before this thing hits the floor, all of that gravitational potential energy will have become kinetic energy. So it sounds like something's being conserved, and we'll talk about that later as well. Okay, this is the formula for gravitational potential energy. So we use U for potential energy. There's different types of potential energy, so I'm going to put G for gravity. It's the mass of the object times the acceleration due to gravity times the height of the object. There's also like spring potential energy, right? If you set a spring, you know, it has spring potential energy, or elastic potential energy, or something like that. Let's see. Now, here, oh boy. How can we change the energy of a system? How can we change the energy of a system? So let's say that, what do you know? All right, so let's say that the eraser is the system. All right, so that's the system, and everything else is the environment. Now, how can I change the energy of that system? Just think about it for a minute. Think about it. What can I do? Ugh, it wasn't supposed to happen. Come on, be nice. Better hurry up, right? Oh, come on. Okay, we'll just do it like that. Cheat, right? Ugh. Okay, so how can I change the energy of the system? Real simple. Bang! Oh, sorry. All right? So that's what you have to do, okay? So how do you change the energy of a system? You apply a force to it, right? You apply a force to it. And that's another way of saying you do work on it. So here. So you know, I was in the environment, right? And I applied a force. I did work on it. And so I added energy to that system, right? The eraser. And so the environment can add energy. The environment can also remove energy. Now notice, I did work, right? We're not going to talk about heat. That's thermodynamics, and they talk about that in chemistry, and we're not going to talk about it. So please ignore the heat, okay? So again, if we can add energy to the system, it stands to reason that we can remove energy from the system. So what's a nice example of that? Well, here's a hill, and let's say we have a bicyclist, whatever, I don't know, riding up a hill. Well, if the bicyclist is the system and everything else is the environment adding energy or removing energy as that poor cyclist goes up the hill? It's removing, right? So that's removing energy. The environment is removing energy from the system. But here, okay, here the cyclist is going down the hill. So what's the environment doing? It's adding energy to the system. So that's, all right, so that's the thing, right? So energy can be added to the system by the environment. Energy can be removed from the system by the environment. All right. So this is called the energy principle. What we've been talking about is called the energy principle. Can I have my eraser back? You can just throw it. How do you like that? Thank you. Okay, good shot. Okay, so this is the energy principle. So the change in energy of a system equals the external work. So you can add or you can subtract, right? In, out. Okay, so look, if we add energy, what's the sign of delta cis? Positive. So what's the sign of the work? Positive. If we subtract energy, we take out energy, that means that this is negative, so it has to be the sign of the work, negative. So work can be positive, can be negative, can be zero too, you know. Okay, so here we go. Oh my gosh. All right, this is the basic energy model. And we'll talk more about this as we continue on. So energy is a property of a system. That's the important thing, system. Energy is transformed within the system without loss. So we see kinetic going to potential or potential going to kinetic, or that's thermal. We'll talk about that later. Energy is transferred to and from the system by forces from the environment. See the difference? Transformed from one particular type of energy to another, but transferred, it's environment to system or system to the environment. Different. Okay, energy is transferred to and from the system by forces from the environment, like gravity going up and down a hill. The forces do work on the system. The work is positive for energy added, like you're riding a bike down a hill. Work is negative for energy removed. You're riding a bike up the hill, right? Gravity makes it difficult. Okay. The energy of an isolated system, one that doesn't interact with its environment, does not change. It's conserved. And we're going to talk a lot about that next chapter. So that's what it means to be conserved. It doesn't change. The energy principle is delta E sys equals W external. And yeah, the model fails if there's energy transfer via thermal processes, heat. We're just not going to talk about that. Simple as that. Okay. All right. So, you know, I hit that eraser, right? I did work on the eraser, and I changed its kinetic energy. Well, we want to develop an equation that relates the work to the kinetic energy. And I don't usually do derivations in class because I figure you can read it in a book, but this is a worthwhile one we're going to do. Okay? So we're just going to do one-dimensional motion. So we're going to imagine a particle is moving along the x-axis. So what's the most important equation in all of classical physics? F equals ma. Right? So F equals ma. Good place to start, right? We know it's true, you know. All right, F equals ma. Now, if I feel like it, you know, what do you learn in math? If you do something to the left-hand side of an equation, you can do it to the right-hand side, right? So I'm going to multiply both sides of this equation by dx. Well, whatever, you know. So F dx equals ma dx. Okay, whoopee! All right, now, whenever you see an equation with like a dx or a dt or a dy, I mean, you know, what do you usually do to an equation like that? You usually integrate it, right? I mean, that's sort of reasonable. So again, you're doing the same thing to both sides, so it's totally legal, right? Totally legal. And we're only dealing with one-dimensional motion, so I'm going to put a little x here, all right? Because the force is in the x direction, and just like the A is in the x direction. Not a big deal. Okay, now let's play around with this. Okay, so first of all, the mass is constant. We can pull it out. Second of all, what's A? What's the definition of A? It's dv dt. All right, so I pull the m out. A is dv dt. Then I have a dx. Now, you know, I can change the order of, I can write this however I want to, right? So let's write it a little bit differently. So I have m integral. Now what's dx dt? Dx dt is just, let me make that, is just v, right? It's just v, you know? So dx dt is v. So I'm going to put that here, put a little subscript. So dx dt is v, and then I have a dvx. And you know, I'm going from some initial velocity to some final velocity, right? Now, what's that? What's the integral of v dv? Well, I mean, what's this? What's the integral of dx dx? It's x squared over 2, right? So what's the integral of v dv? It's m. It's just v squared over 2, right? But that's from some initial state to some final state. So that's m v final squared over 2 minus mv initial squared over 2. Okay? Now, somewhere along the line, oh, yeah. So what I just proved is this. Now, here's the thing. This, okay, so kinetic energy, the energy of motion, is defined to be 1/2 mv squared. Or if you want to write it, mv squared over 2. Same thing, right? So what is this? 1/2 mv squared, but it's final. So this is the final kinetic energy. So right here, that's K final. This is 1/2 V initial squared. That's K initial. Now, what's this thing? This is that horrible 4-letter word, work. Right? That's the definition of work. Okay? So be careful. Work is done by a force, right? There's an F there. So work is done by a force on an object, and the object moves some distance dx. It has to move, you know? If it doesn't move, dx would be 0, and the work would be 0. All right, so let me repeat myself. Work is always done by a force acting on an object, and the object has to move if there's work. Okay. All right, so how can we write this? You know, how can we write this? Well, this is K final minus K initial. That's just the change in kinetic energy, right? So yeah, and this is external work, by the way, or the total work. So the net work, the total work, equals the change in kinetic energy. And you're going to see that this is an incredibly useful equation to solve a lot of problems. I mean, it's nice, short, and sweet, you know, but it's really, really useful. Now, what are the units? Well, let me just look over here. What are the units of work? So there's a force, so that's a Newton. There's a dx, there's a meter, right? So work has units of Newton meters. And of course, since the work equals the change in kinetic energy, the kinetic energy also has units of Newton meters, okay? Newton meters. Now, you know how it is in physics? There's all these famous dead physicists that you have to honor by naming a unit after them, right? So a Newton meter is called a joule after a guy named Joule, right? So that's how you spell joule. And he did a lot with energy. We'll talk about him later, right? So the units of work or the unit of energy is joule. And joule is just a Newton meter, right? Newton meter. Okay. Okay. What is an integral? In other words, if you have a force plotted versus distance, what's the integral? It's the area under the curve, right? So, you know, so the work here that this force does when it makes an object go from x equals 1 meter to x equals 3 meters, this area here is the work, because the work, I mean, it's the integral is area under the curve. All right, here's a question for you. Oh, let me show you something else real quick, sorry. So the work equals integral f dx. Okay, well, what if the force is constant? Well, if it's constant, you can bring it outside the integral, right? Then you have that. But the sum, this is just a sum of dx's, right? That's just f delta x. And that's what a lot of high school physics classes teach, you know, that don't have calculus. They just say that the work is the force times the distance. But that's only true, again, if the force is constant, you know. All right, let's have you answer a question now. In 2012, 18-year-old Zoe Williams smashed a British record by lifting 121 kilograms. By the way, that's 266 pounds. Twice her body weight. At the moment shown in the photo, how much work is she doing on the barbell? The vertical distance between the floor and the barbell is 2 meters. So use what we've discussed here and pause your video and answer the question. All right. Well, the question asks for the work. Work is integral f dx. All right, so there's a lot of force, right? I mean, she's really strong, twice her body weight. However, what's the dx? I mean, she's holding it still. So what's dx? It's 0. So even so, she's really in a lot of pain, I'm sure. According to the definition of physics, work, she is not doing any work at all. Okay? So remember that. Integral f dx. The object has to move. So if I'm pushing on this whiteboard, you know, and I'm getting tired, my muscles are starting to get achy and sore, and I'm sweating like a dog or something like that. If it's not moving, I'm not doing any work. So just be aware of that. Okay. Let's go back to work. So again, work can be positive, work can be negative, or it can actually be 0, you know. So, yeah. So we want to talk about work. We want to reconsider our definition because it's not complete, right? All we have is this. It's really not complete because, you know, when I did this derivation, I just said that we had a particle moving along the line, right, along the x-axis. Well, what if it's doing something else? So we want to expand our definition of work. Okay, so here we go. Oh, let me remind you of something first. So what did we learn a long time ago? If the acceleration has the same sign, which means direction, as the velocity, does the speed of the particle increase, decrease, or what? I hope you remember this, right? The speed increases. On the other hand, if the acceleration and velocity have opposite signs or opposite directions, what do you say? The thing is slowing down. Okay? All right. So you're supposed to know that by now, but I just wanted to remind you. Okay. So here, okay, so the force is in that direction. Well, F equals ma. It means that the acceleration is in that direction, right? All right. But anyway, so let's see. So something's moving to the right. Then we apply a force to the right. So what's going to happen to the speed of the object? Sort of obvious, right? It's going to increase, right? It's going to increase. All right, that one. Okay, so therefore, if the speed increases, that means the kinetic energy increases, right? 1/2 mv squared. So the kinetic energy increases, so it has to be the sign of the work. Positive. Agree? Positive. Because this is positive, so that's positive. And we already said that, right? You know, if the bicycle is going down a hill, right? Positive, the gravity is doing, or the environment is doing a positive work, it's making it go faster, you know? Okay, here's a situation. Okay, now acceleration or force is this way, velocity is that way, so we know what's going to happen because we learned about it a long time ago. But now we're talking about work, right? Okay, so will the speed of the object increase, decrease, or remain constant? Well, it's sort of obvious, right? If something's going this way, then we smack it that way, it's going to slow down, right? Okay, so the speed will decrease, or you can just think of this. The speed will decrease. So that means that the final speed is less than the initial speed, so the final kinetic energy is less than the initial kinetic energy. So this is negative. So therefore, what has to be the sign of W net, or the work? Negative. Kind of makes sense. Okay, one more. So here we have a table, and we're moving something along the table. So the velocity is this way. And then there's some force which is perpendicular to the velocity. So is this force going to be able to change the velocity? What do you think? I don't have a table here, I can't show you, sorry, but it doesn't, right? I mean, think about it. If we had a table here, and I was just pushing something along, I mean, you know, gravity is perpendicular, right, to the direction of the velocity. Does gravity make it go faster or slower? No, it's perpendicular. How can it, you know? Ridiculous. Okay, so when the velocity and the force are perpendicular, the speed does not change, okay? So the speed does not change. Well, if the speed doesn't change, what's delta K? 0, right? There's no change. So therefore, what's the external work or the net work? 0, all right? Okay, so work can be positive, it can be negative, it can be 0. Well, here's our definition for one-dimensional motion. We got to fix it, you know, because we got to use some kind of a mathematical operation so it can be positive, negative, or 0. All right, so we have to invent a new mathematical operation. Now you notice, I mean, I didn't write it because we were just doing one dimension, but you know, F is force is a vector, right? Dx is a vector. So we're really multiplying two vectors. And, but not just that though, I mean, yeah, we're multiplying two vectors, but is this a vector or a scalar? Well, it's kinetic energy, right? 1/2 mv squared. That's a scalar, you know? So we're multiplying two vectors, and we have to be able to get positive, negative, or 0, and the answer has to be a scalar. So we've got to invent something called scalar product. So we're multiplying two vectors, we're getting a scalar, and it has to be able to be positive, negative, or 0. Okay, so here we go. And some of you have seen this before, and some of you haven't. So I'm just assuming you haven't, so we're starting from scratch. All right, so what we're learning is how to multiply two vectors when the result is a scalar. So the symbol for it is a dot. So some people call this dot product because of the dot. Some people call it a scalar product because the answer is a scalar, right? It's not a vector. So call it whatever you like, dot or scalar. Okay, so here's vector A, here's vector B. There's an angle theta between them. So, you know, if you want to, you can write A in terms of the I, J, and K, right? So A is AX times I, AY times J, AZ times K. Same thing for B, you know, right in terms of I, J, and K. All right, and so here's how you define, well, there's really two ways to define it. This is the first way. So A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. So we just write that AB cos theta, right? So that's one way to do it, AB cos theta. Now, let's explore that a little bit. So where are you going to get your maximum? For what angle is going to give you your maximum dot product? Well, it should be obvious, right? Maximum happens when theta equals 0 degrees. Because what's cosine of 0? 1, right? Cosine goes between -1 and +1. So you're going to get your maximum when theta is 0. Now think of work, right? If we have velocity this way, or dx that way, I guess, and we have a force that way, it's not going to be the biggest change in kinetic energy? Well, yeah, right? So the biggest work. Okay, so we get our maximum when theta equals 0, and then we're just going to have A dot B just equals AB, right? Because cosine theta is 1. Where are we going to have our, where's it going to be 0? Where's the dot product going to be 0? So in other words, cosine of what is 0? 90. So theta equals 90 degrees. So now we're going to have A dot B equals 0. So that's a situation where we had something moving on a table, and then so there's the velocity, and we had the force perpendicular. And what was did it change the speed? No, it didn't change the speed at all, right? So the work was 0, remember? The work was 0. So that's 0. Now, where are you going to have your minimum? Well, so the cosine, again, cosine goes between 1 and -1. So what angle do you get -1? 180. So theta equals 180 degrees. So A dot B equals AB cos 180. Cos 180 is -1, so you get negative AB. All right, so that's one way to calculate the dot product. Just say AB cos theta. But again, you know, you're going to use this if you know what the magnitude of A is, and if you know what the magnitude of B is, and if you know the angle between them, right? Well, what if you don't, you know? What if you don't? Well, if you don't know the angle between them and you don't want to figure it out, you can just use this method. So another way to calculate it, A dot B, you just multiply the x components, AX, BX, multiply the y components, AY, BY, multiply the z's, AZ, BZ, and add them all up. So, you know, if you have your vectors in terms like this, then it'd probably be easier to do this one. On the other hand, if you know the magnitudes and the angle, you're going to use that one. So just, you know, use whatever you like. Okay, so how do you learn this? Practice. Okay, so I gave you the definitions, and here you have components, right? So no, you're going to use this one, right? You can use this definition. So please pause your video and figure this out. Okay, let's get back. All right, so using this definition, let's do it. All right, so AX is 1, BX is 2. So we have 1 times 2. All right. AY is 2, BY is 1. So we have 2 times 1. And then AZ is 1K, and this is minus 3K. So it's 1 times minus 3. So 2 plus 2 is 4, minus 3 is 1. So the answer is 1. So make sure you do that, because we're going to be using dot products a lot. All right, so why did we learn all this dot product? So we can get a good definition of work. So here is the complete definition of work. So it's a dot product, right? So when this is parallel to this, the angle is 0, and it's a maximum. When this is perpendicular to this, it's 0. When this is anti-parallel, it's negative, right? So all that plus minus 0 business is incorporated into this definition now because we have the dot product. So it's great. And that's a good place to quit.